Okay, so we didn't finish, I just want to finish up just a couple quick things from continuous functions. You know what, let's not worry about that page. What's wrong? No, I'm not going to ask you about composite functions.
Can we not do step functions ever?
Okay, so intermediate value theorem,
What we just did.
okay, for continuous functions. Basically what we're saying, take a function, okay, it starts here and ends here, sorry.
So we just give you theorems.
So should I cross that out?
Not the first part. The first part was the rules, but the second one, don't worry about example 4. I won't ask you about that one.
Ever?
Oh God, that's an oscillating.
All right, intermediate value theorem says basically here's a point. Hold on. Here's a point f of a. Why is this not working? Hold on. My pen. What happened to my pen?
Do you want me to write?
So cowardly.
Okay, I'll explain here. If you have, here's A, right, here's a value of A, here's a value of B. So this is f of A here, and this is f of B. Basically, intermediate value theorem says if you have a continuous function, then it has to hit all the points in between f of A and f of B. In other words, it can't skip over a y value. Otherwise, it means there would be a jump or a hole in the graph or an asymptote or something. If it's continuous from A to B, then it has to hit all the y values in between. Okay? Right. So you had an example like this on your homework where you have a piecewise function and you want to make sure that it's continuous. So here it's defined for x less than or equal to 2, and then this part is from x greater than 2. What would we want to do to make sure that it's continuous, Luke?
Like,
Plug in.
Plug in 2 for
And then
x.
7 equals.
Okay, so go ahead and do that.
Int a is 3. What? Sorry.
You didn't just do it before us. No way.
Because remember, from the left and from the right, if we were to look at the left-hand limit, that would be this. Our left-hand limit gives us 7. Our right-hand limit, okay, so this is the limit as x approaches 2 from the left. And this is the limit as x approaches 2 from the right. We want to make sure that those are equal to each other. That's what we need to have. And then we have a equals 3. Okay. And again, all you would need to do is put 3 in for A, graph it on your calculator, and you would be able to see that they have to match up, that they would match up. Okay. Just if you wanted to check on your calculator, plug 2 in here for A. So one of them would be 2x plus 3 when x is less than or equal to 2.
and then they would.
And then the other one, and then you could see,
The other one would have to be like 3, right? Since it says it has to be greater than 2.
so here we have 2x plus 3. And then this one, we obviously don't want to use A. We're going to use, what do we get for A? 3. So we have 3x plus 1. And this is going to be x greater than 2.
Why does the easy stuff have to come at the end?
And
We
then
learn the hard stuff.
if you graph it, hopefully when we graph, they connect. Ignore that line. This one just has, it's these two that you're looking at.
Oh, wow, they do connect.
It's something, your calculator doesn't do this much for whatever reason when it does piecewise function, but the blue and the red line, they connect, so we know that it's going to be continuous. And you can also double check with the table. All right, we're gonna move on to 2-4 now.
Ooh, okay. That's all it was?
That was all that we didn't finish.
Wow. No, yeah, okay. That was easy.
That was easy.
Yeah.
All right, average rate of change and tangent lines. Okay, so average rate of change, right here, very important in calculus. So we'll have average rate of change and then we'll have instantaneous rate of change. Average rate of change, you need 2 points. If you look at this formula, this is basically slope. Right, this is average speed. So we talked a little bit about this. Okay. So when we have average rate of change, it's like y2 minus y1 over x2 minus x1. I'm just using t for time, so it's over a time interval. So if you kind of imagine the time interval would go from t1 to t2. So you just plug it into whatever function you might have. Got it? So our first example, let's say, we'll talk a lot about like particle motion in this class and things like that. So imagine there's a particle moving along this curve. And it's going, we want to look at from 0 to 4. So I'm really looking at from here to here on the graph.
Why?
It's just, that's what I gave. That's what I gave you. I could have given you a different domain. If I had given you maybe from -0.5 to 6, we would have used different points. So your average rate of change is going to change. It's going to change depending on the interval that you're working with. So,
is your assumption that your x-axis is time?
yes, that's what we'll work with later.
How is there a negative? On your
Well, that's why
graph?
we're just using this example. Yeah, you're right. When we work with time, we don't work with negative values. But for right now, we can have average rate of change with a negative value. That's fine.
What if this is in a distance?
That was really cool though. Look into how it says at a specific point, like if you wanted to find this exactly at 2 seconds, there's actually no time there because you know it's just like acting from itself.
We'll get to that. Okay, so we want f of 4 minus f of 0 over 4 minus 0. I think this is t1, this is t2. Good? So what's our function? Well, it's square root of 2x plus 1. So just plug in 4. So we get square root of 9,
Wait.
right? Minus, right, 4 here, you get 2 times 4 is 8 plus 1. Yeah, okay, so I gave you an example with an x and a y axis, but normally what we would have, this would be x is like time.
Or like seconds or something.
Right, and y is still going to be a y.
Okay.
So,
All right, so we get 3 minus 1 over 3, so we get,
Why is it 4 minus 1?
oh, sorry, that's supposed to be a 0. Thank you.
wait, why is it root 9? Because you plugged it into the actual.
Why do I keep writing the wrong? You see it now?
Yeah. So it should be 3/4. Or 2. No, 1/2.
So we get 1/2. Okay, so what that means here, I gave you the graph, but you won't always have the graph right there. If you want to think about this from a geometric perspective,
The tangent line.
not quite.
Oh.
Okay, this is actually the secant. So one of the things back in geometry when you learn about secants versus tangents of a circle, a secant line goes through 2 points, whereas the tangent just hits the curve at 1 point, or a circle at 1 point.
Wait, does the secant,
So-
to split it in half, or could the secant just be any 2 points of the circle?
It can be, a secant can hit through any 2 points on the circle.
Could potentially
But when we
split
look at a curve, I'm going to tell you where I want you to. So in this case, I told you to use 0 and 4. Now, if you were to just count using rise over run, you would see that it's 1/2. Okay, so that's the average rate of change is the slope of that line connecting the 2 points. Okay with that?
Oh, so it's just.
It's 1/2.
y over x.
It's the average, we call it the average rate of change because this is a curve, which means the rate at which it's changing is going to be different depending on which points I'm using. So if I had chosen maybe 4 to 8, what's going to happen with my slope?
It's different.
it's gonna be different. It's not gonna be 1/2, it's probably gonna be something smaller, cause we know the square root kinda, it still goes to infinity, but it does start to become a little more horizontal. Let's look at the next example. Okay, so we have 2 plus sine of t from 0 to pi. So I want f of pi minus f of 0 over pi minus 0. So here's 0. Over here is pi.
So isn't it?
Okay, so you might be able to see this from a geometric perspective, like I was saying. If you kind of look at this line here, it's got a slope of 0. So let's just confirm that. So if I plug in pi, I have 2 plus sine of pi, right? And then if I plug in 0, I have 2 plus sine of 0. Well, what's sine of pi?
1,
Try again.
0.
0. So I have 2 plus 0. And what's sine of 0?
1, 0.
0. So I have 0 over pi, which is 0. Which confirms what we were kind of predicting in the beginning by just looking at the line that goes through those 2 points. It makes sense. So the average rate of change, again, we're talking about the average slope, so it kind of goes up and then it comes back down. So it makes sense that the average would be straight through.
But it'll get harder than these two to the point where you can't just like count, go rise over.
Correct. Which leads us to the next page.
Everything is too good to be
Too good to be true.
great.
No, this is good though.
Wait, can
This
you
is
go
good.
back for a second?
Yeah.
I wasn't done with my.
You're fine.
Sine x over x is 1, though, right?
Can I come to you tomorrow during
I have my AP during bonus.
How can you turn on us?
Sorry.
We
I'll be here early.
Here you go, Maya.
I'll be here. Oh, I have a club meeting at lunch.
Thanks.
Yeah,
What club's
So I'll
what
come
club are you
early.
involved with? Oh,
Paul,
God.
the animal.
We'll talk later.
Wait,
By force?
question. So can I come early? Like 7:30?
Oh, it's that special
Okay.
like.
I'm setting my alarm early, just for
Okay.
you.
It's not-
All right,
You
so
don't have recycling.
No, but it's in bonus in the green class. Sorry, you have a green. What? I don't know.
okay, the figure below.
Yeah. Yeah, I don't think public.
The figure below shows the growth of a fruit fly population in a controlled experiment. So we want to compute the average rate of the average change and the slope of the secant line PQ. So here's P and here's Q. Okay? Here's my curve. So look at the curve between those 2 points. We're going to find the average rate of change,
That line is the secant.
and that's the secant line, correct?
So can't you just look at the
So-
secant line and say that the slope is?
Right, now kind of ignore, there's information here that I didn't want to just, you can copy and you can kind of see the answer here, but let's just work it out. So that delta P, so delta P over delta T. So that's the change in population. So that's going to be 340
Where did you get that?
right here
Oh.
and here. So we're taking these 2 points and we're going to find the slope. So 340 minus 150 over 45 minus 23.
It's like y minus y over x minus x.
So we're just gonna, if somebody have a calculator
Yeah.
to do that?
The first one's approximately 190 over 718.
Over 20.
Over 22.
22.
Which comes out to be
It should be like
8.9?
8.636.
636. 9? It's 8.6? Okay. So the secant slope is the same result. Okay, we would have found the secant slope the same way.
Can you please teach us how to do this count?
What do you mean the same?
It's like,
Oh,
Okay, because average rate of change, I kind of explained it to you on the previous page. I didn't want you to have to redo it again here. The secant slope and the average rate of change are the same thing. So these two,
So it's 8.6 also.
so sometimes I'll ask you for the secant slope and sometimes I'll ask you for the average rate of change. You need to know that I'm referring to the same question, basically. And that's what I have right here. So average rate of change is the same as the slope of the secant line, slope of the secant line. Okay, one more thing, and then it'll be time to go. I'll just kind of explain this, and then we'll actually apply it tomorrow's class. You'll be able to do the first few problems because they're on average rate of change, but you won't be able to get too far. Okay, tangent to a curve. Okay. Tangent to a curve. So we want to come up with a formula to come up with that tangent. We know how to find the slope with 2 lines, or 2 points, excuse me. But how do we find the slope with just 1 point?
Can you use
Okay.
0 as the, no problem.
Can't use, so here we go. So here's our 2 points. So basically what we're going to do is we're going to move one of these, we're going to move the 2 points closer and closer to each other. Okay, so right now they're pretty spread out.
Like mathematically or?
Mathematically, we're going to move them closer and closer together. So basically what we're saying is we're going to move, imagine if we moved Q closer and closer to point P. So do you see this,
On the curve
this
or closer?
pink line here, right here?
That's a tangent.
That's the tangent. So if I keep moving Q closer and closer,
You're gonna get both, it's gonna become a secant line.
the secant line is going to turn into a tangent line. And the way we do that is we're going to use limits. So we're going to basically look at what happens. So this H just means how far away it is from the original. So if I have a point that's starting at A, and then I want to look at A plus H, so as H gets closer to 0, so maybe this point is, you know, whatever it might be. It could be 3, 1. And then maybe I look at 3.01, 3.001. So as I move that closer and closer to the original, I will get the slope of the tangent line. And that is what we will do tomorrow.
Good. Whoa, that went by very quickly.
Okay, no, I'm sure if you want.